तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next one. Before we do that, we would recapitulate what we learned in the previous lecture. You might recall we discussed about the various mathematical operations that can be performed with operational amplifiers. In the last lecture, we saw how the mathematical operation of differentiation can be performed using the operational amplifier, and we also saw some applications of these different mathematical operations like summing, integration, differentiation, etc. The two examples that we discussed are basically solving simultaneous equations using operational amplifiers, and also I gave an example of a simple second order differential equation corresponding to the including the damping factor. We discussed how that equation can be solved by using a set of integrators and providing feedback, you might recall. In this lecture, we would like to go into the actual characteristics of the operational amplifier. From the time we discussed about operational amplifiers, we immediately talked about the importance of negative feedback and different application circuits based on negative feedback. Afterwards, we saw why the name operational amplifier has come to stay, and in that we discussed about the different mathematical operations that can be performed and some of the applications. So we are now basically coming to look at the operational amplifier as a device and see what are its basic characteristics which help us to perform different circuit functions using operational amplifier. I have just listed out in the screen the different characteristics of the op amp. I have not exhaustively included all the characteristics, but I have put the most important characteristics of an operational amplifier. So if you can see on the screen, the first characteristic is called the input offset voltage, then you have the input bias current, the input resistance, which is a very important characteristic for any amplifier, the open loop voltage gain, which is actually the large gain that is obtained without providing any feedback. Then there is a quantity called a CMRR, which is common mode rejection ratio, which is also a very important characteristic of differential amplifier, and operational amplifier being a differential amplifier, it has got this important characteristic. Then we also would see the gain bandwidth product, how it is a constant. So and also the last one, which is the slew rate. So what we would do perhaps is to take each one of these characteristics and define what we mean by the various characteristics and how do we measure for a given operational amplifier each of these characteristics. Usually the manufacturer, if you look at the data manual, looking at the data manual is a very important step in doing electronics. So for an operational amplifier, if you look at the manufacturer's data manual, the manufacturer is most anxious to make you understand about the complete characteristics of the op amp, so that you will be able to exploit these characteristics in different application circuits. And therefore, the manufacturer data manual is a very important document for anybody who wants to practice practical electronics. So, if you look at them, you would find for under each one of these different characteristics that I have listed now, you would find they would give the corresponding numbers for the operational amplifier that you are looking at. As an example, if it is for example 741, which is the most popular operational amplifier that we have been using also, you would find the various parameters like input offset voltage, the CMRR, the open loop voltage gain, etc., or all will be listed in the data manual, so that when we measure, we can also see whether they correspond to what the manufacturer himself claims as a corresponding quantity. We also should perhaps bear in mind that these characteristics are very specific to the DC conditions that you provide. For example, what the power supply voltage that you use and what is the operating frequency and things like that. So, usually the manufacturer will also mention the operating conditions, the temperature, the various power supply voltages, the signal frequency, etc., before they specify the various characteristics. So, we should also bear in mind that the characteristics can vary slightly when we change these conditions like the power supply voltage and things like that. So, with this background, let us perhaps move on to the first of the different characteristics, which is input offset voltage. Now, there are two things that you normally worry about when it comes to the input side of an operational amplifier with reference to offset, and that is the offset current and the offset voltage. You also have two different type of offset voltages with reference to the input offset voltage and the output offset voltage. So, we should try to understand the meaning of all these terms before we go into the actual measurement and things like that. So, what we normally expect in any amplifier, if it is a linear amplifier, that means if the output is proportional to the input, that is what we mean by linear operational amplifier, then if I connect 0 voltage at the input, the signal is 0. If I apply 0 voltage, the output should obviously be 0 also. But you would find in a practical operational amplifier or any amplifier for that matter, even when you give 0 input, which corresponds to connecting the input terminal to the ground potential, even when you give 0 input, you would find invariably there will be a very small but finite voltage at the output. So, that means what? Without giving any input, you seem to be getting an output, even though small. So, this output that you get when you make the input voltage 0 is what is called output offset voltage of the amplifier. So, this of course, as I already mentioned to you, will depend upon the applied power supply voltage and various other conditions, environmental conditions. So, for example, I have indicated here, if one connected 0 volts to both the inputs of an op amp and measured 30 millivolts DC at the output, then this 30 millivolts of unwanted voltage generated by the circuit itself, by the operational amplifier circuit itself, without any input, is what is called the output offset voltage of the amplifier. You can also look at it in another way. Why are you getting an output offset voltage? Why are you getting an output voltage? There should be an input voltage if the amplifier is a good one. So, you can imagine that this output voltage, for example, that 30 millivolts that I was talking to you about, has come about because of some spurious input voltage that has come, which when amplified by the gain of the amplifier corresponding to the configuration that you use, then that is the reason why you are getting the output offset voltage. You can take that stand. If you do that, then you must give another voltage at the input which is opposite to this voltage source, which will only make the output 0. That means, if I want to make the output voltage 0, I must give an input voltage in a proper polarity, so that it takes care of the spurious input sources that might be there, which is responsible for the output voltage. So, how we normally define the input offset voltage is by saying that it is the input voltage that I should apply at any one of the two inputs in the case of the operational amplifier to make the output 0. This is what we call output input offset voltage. This input voltage, because it is an opposite polarity, will nullify whatever spurious input voltage that you have without connecting anything. So that the total input voltage becomes 0, and when you multiply that by the gain of the amplifier, the output voltage is also 0, because anything multiplied by 0 is 0. Right. So, the manufacturers, as I already mentioned to you, invariably specifies an input offset voltage for the amplifier, and normally the output offset voltage can be calculated by looking at the gain of the amplifier. The gain of the amplifier, you know, will depend upon the configuration that you use. If it is a inverting amplifier, the gain is minus Rf by R2 by R1 or minus Rf by Ri. We have already seen this in the earlier lectures. And if it is a non-inverting amplifier, the gain is 1 plus R2 by R1, where R2 is a feedback resistor, and therefore we know for a given configuration what is the gain. And if we know what is the input offset voltage, you multiply the input offset voltage by the gain, that will be the output offset voltage of the amplifier. So, let us now look at the output offset voltage in much more general terms. I have already explained to you that the output offset voltage can be shown to be due to some spurious input voltage which has come due to some imbalances inside the amplifier configuration. There is also another source for the output offset voltage. Apart from this input offset voltage, it can come about due to another reason also, and that reason is you have two input terminals for a given operational amplifiers. If you look at the inverting and the non-inverting amplifiers, if you actually go into the amplifier through those terminals, you would find you are actually entering into the base of two transistors connected in a differential amplifier configuration. So, the two inverting and non-inverting amplifier terminals are basically the terminals of two bases of the two transistors which are connected immediately at the input stage as a differential amplifier. So, you always know if an amplifier should work, there should be a finite current flowing into the base of the transistor, then only the transistor can act as an amplifier. So, you require a minimum current. This minimum current we call the bias current. We have already talked about the biasing of transistors and all that in some earlier lectures, you may recall, and therefore, there should be some finite but minimum current flowing through the input terminals of an op amp to make the op amp work as an amplifier. These input currents are called input bias currents. They will be very small compared to the normal currents that you will be discussing in a given circuit, and therefore, you do have two currents at the two input terminals of an operational amplifier. So, if in principle, if the amplifier is designed in a best manner, then you would expect, because it is a difference amplifier, it is always sensitive to the difference in the two currents. So, you would always expect if the offset voltage of an amplifier should be 0, then these two input bias currents which flow into the two terminals should be equal. But the two input bias currents are equal only in an ideal case. In a normal amplifier, you would find there will be always some finite but small difference in the two input bias currents. So, this difference in the bias currents also can cause a differential voltage at the input, which again can be amplified by the gain of the amplifier, and therefore, the output offset voltage can also arise from this difference in the two input bias currents. So, the difference in the input bias currents is called input bias current offset. Therefore, in principle, if you do not apply any signal at the inputs of an operational amplifier, we observed but that we can also still measure a finite but small voltage at the output of the amplifier. This output offset voltage, as we call it, has got two contributions, one from the spurious source that we already discussed about at the input source, at the input side, which is called the input offset voltage. The second one is due to the difference in the bias currents at the two input terminals of an operational amplifier, which is responsible for providing additional differential voltage at the input, which again gets amplified and comes out as an output offset voltage. Now, before we go further, let us understand about the input offset voltage. The manufacturer specifies usually the input offset voltage for a given amplifier under certain operating conditions. So, if I call that VIO, and if I for example choose a configuration that we are all familiar with, namely the non-inverting amplifier. You can see on the screen on the right side I have shown a non-inverting amplifier with RF and RI, and the input terminal is connected to ground for corresponding to the inverting terminal. That VIO, I assume, is something like a battery which has been connected at the input corresponding to the plus terminal. So, if you know this circuit, we can calculate what is the output voltage. What is the output voltage? It is the gain times A is the gain, A times V in, the voltage impressed at the input. And what is that V in? The V in now is actually VIO, that is there, plus some voltage which got amplified due to the amplifier, which is corresponding to R1 divided by R1 plus RF times V output. That is, we are trying to calculate what will be the input voltage if I have VO at the output. So, VO is multiplied by 1 by gain, this R1 plus RF by R1 is the gain, and so it is put in a inversion here, R1 divided by R1 plus RF, and therefore, this gives you the input voltage that you would get corresponding to the output that you measure. The combination of this is what you will measure as the output. So, if I simplify this, you can see VO is equal to VIO, this VIO multiplied by A divided by 1 plus A within bracket R1 by R1 plus RF. What I have done is I have rearranged all the terminals corresponding to VO and then rewritten this mathematical expression simplified. Therefore, the output voltage is VIO divided by this quantity, because that 1 is very small compared to the second in the denominator, and therefore, this second term will dominate most of the time, and therefore, VIO is into A by A into R1 plus R1 divided by R1 plus RF is expression effectively for the output voltage. So, that this output voltage is what we call the output offset voltage. Therefore, in the next equation I have written VO offset is nothing but VIO into 1 R1 plus RF by R1, because these two A will cancel and the denominator in the denominator will go to the numerator. So, VIO into R1 plus RF by R1 is the output offset voltage. So, this equation gives you a method of measuring or calculating the output offset voltage for a given configuration. In this configuration, it is a non-inverting configuration. Therefore, 1 plus RF by R1 is the gain of the amplifier, we all know, and that is what I have written here. R1 plus RF by R1 is nothing but 1 plus RF by R1. So, you multiply the input offset voltage by the gain, that is what you get as the output offset voltage. Let us now try to take a simple illustrative example as a small problem and try to understand how we can calculate the input output offset voltage or input offset voltage, as the case may be. So, I have given some specific numbers here. I have RF is 1 mega ohm in the circuit, 100 kilo ohm is the R1 value, and I now measure the output voltage. So, because RF is 1 mega ohm, this is 10, so the gain is about 10, the gain of the amplifier is 10. So, if the output voltage that I measure is 40.4 millivolt, I just measure the output voltage using a multimeter for this configuration, then I can calculate what should be the input offset voltage, because I know the gain and I know the output voltage. Output voltage divided by gain gives me the input voltage, because output voltage is nothing but input voltage multiplied by the gain. So, Vi, in this case it is actually VIO, the input offset voltage is 40.4 divided by 10, because the 10 is the gain, and that is 4.04 millivolt, which is reasonably a small value for most of the practical applications, and therefore, the input offset voltage for a given configuration can be measured by constructing the amplifier and measuring the output voltage and divide the output voltage by the corresponding gain of the configuration. That should give me the input offset voltage. Now, I will actually perform the experiment and show you and perform the measurement on a given circuit, which I actually shown you just now, and let us see what is the typical output offset voltage and the corresponding input offset voltage. Here you have the circuit for measuring the input offset voltage. You can see it is the same circuit which we used a moment ago. You have the 741 op amp, you have the RF 1 mega ohm and R1 100 kilo ohm, and both the inputs are grounded. The same circuit is wired here on the breadboard. You have the op amp, you have the two resistors when you come closer and see, and the wiring is done with, this is the dual supply behind, and so the wiring is corresponding to the plus, minus and the ground are connected here, and you have the pin number 6 is connected to the multimeter here, which will measure the output voltage. The two input terminals are grounded as you have seen here, and now let us see what is the reading in the multimeter. You can see the multimeter is in 200 millivolts range, corresponding to this point, 200 millivolts range. In that it is measuring 0.9 millivolt. That means the output offset voltage measured by the multimeter is 0.9 millivolt, and the gain of the amplifier, as you have seen, is 10, because this is 1 mega ohm on the feedback, 100 kilo ohm. So, 1000 kilo ohm divided by 100 kilo ohm is approximately 10. Okay, so if I now take 9 millivolts divided by 10, that gives 0.9 millivolt or 900 microvolt, and that is the input offset voltage of this operational amplifier. So, all that you have to do is construct the amplifier, measure the output voltage, divide that by the gain, and what you get is the input offset voltage. So, you saw how the input offset voltage can be measured in the laboratory for a given configuration by actually constructing an amplifier, measuring the output voltage, and then dividing by the gain. You will be able to evaluate the input offset voltage. You can verify whatever value you get with the value given by the manufacturer in the data manual. Right. Now, I also mentioned to you that the output offset voltage has got two contributions. One that we have already seen is due to the finite input offset voltage, and the second is due to the difference in the two bias currents at the two input terminals of the operational amplifier. So, we have to now perhaps find out what will be this offset current. We should first measure the bias currents in a given typical case and see whether the bias currents are equal or unequal. If they are unequal, the difference in the two bias currents is what we call the input offset current. This input offset current flowing through the input resistance of the amplifier can also result in an output voltage which could be part of the output offset voltage. Now I have shown you another circuit on the screen. Again you have RF, R1 and RC, right, and I have shown the two bias currents flowing through the minus and the plus terminals of the operational amplifier 741 here. As usual, this current, bias current, I call I1B, IIB. I is current, this I is input, B is for bias, and I put a minus here because this corresponds to the negative input terminal, the inverting terminal. Similarly, IIB plus corresponds to the input bias current flowing into the non-inverting terminal or the pin number 3 of the 741. So now what will be the output offset voltage due to these two currents is what I am trying to evaluate. So if I now apply the simple superposition theorem, then you can imagine initially you assume that there is only one current flowing and find out what is the output voltage due to that current alone flowing without the other current. Then you bring in the other current, assume the first current is not existing, and then calculate what is the output voltage. Then you perform an algebraic addition of these two voltages by superposition theorem that gives you the total effective output voltage due to the both the bias currents. So if I now in the screen you see VO plus, that corresponds to only the IB plus being present, the input bias current flowing into the non-inverting terminal alone is existing. Therefore if that current is flowing through the resistance RC, you would get a voltage I1B, IB plus into RC. This is a voltage. That voltage will be multiplied by the gain of the amplifier, which is 1 by RF, 1 plus RF by R1. Therefore this gives the output voltage due to only the input bias current flowing through the non-inverting terminal. What about the inverting terminal? If you want to look at the contribution due to IIB minus, then that I call VO minus. The voltage at the output is VO minus due to this current, and that is equal to IIB minus into R1, which is the voltage actually available at this point. The current into resistance gives me the voltage multiplied by the gain of the amplifier. So in that case you can see this is connected to ground, there is no input bias current here, we are considering only the bias current corresponding to the negative terminal or the inverting terminal. Then you find this is nothing but a simple inverting amplifier with a gain minus RF by R1. That is why I have put here minus RF by R1. This is the gain factor, this is a voltage that will be developed across R1 due to the bias current flowing, and so this is the output voltage due to this current. So what we have to do is the total offset voltage due to the two currents IIB plus and IIB minus is nothing but the sum of the two terms that we already got. This is the first term IIB plus into RC multiplied by 1 plus RF by R1 minus, this minus comes because there is a minus in the gain factor because it is an inverting amplifier, minus IIB minus into R1 multiplied by RF by R1. So if you simplify that, you would find, if you simplify this, you can see ultimately you will get an expression RF multiplied by I1 IIB plus minus IIB minus. That shows the output offset voltage is basically due to the difference in the two bias currents. So IIB plus and IIB minus are the difference multiplied by the feedback resistor RF is the responsible for the output offset voltage, which also can be easily understood, I am sure. So this difference IIB plus minus IIB minus is what I call IIO. That means the current at the input which is responsible for the output offset. So IIO is nothing but the input offset current. The input offset current multiplied by RF gives you the offset voltage due to the input bias current. Now after discussing the background theory and all that, it is always useful to look at one simple illustration to understand the concept very clear. So I have given an example here, calculate the offset voltage for the circuit shown below for an op amp specification, which lists input offset current to be 100 nanoamperes. So, the current is a very small quantity, 100 nanoamperes, that is the difference between the two input bias currents. The input bias currents can be slightly higher than this, but the difference is what they are giving as input offset current, and that is 100 nanoamperes. So, how do I calculate? You know, the solution is output offset voltage due to the input offset current is nothing but input offset current multiplied by the feedback resistor, because it becomes a current to voltage converter, as you can see. So, IIO multiplied by RF, where RF here is 1 megohm. So, 100 nanoamperes multiplied by 1 megohm gives me 100 millivolt. So, the offset voltage due to the input bias current offset is 100 millivolt. That is a very simple way of calculating the output offset. So, now what is the total offset due to both VIO and IIO? I already mentioned to you, what you have to do is calculate VIO, calculate IIO, and then you find out what is the voltage output due to VIO and what is the voltage output due to IIO only being present, and then add them together algebraically. That gives you the total offset voltage. We have to take them. So, I have given again one more example in this case, where we can calculate both of them together. Calculate the total offset voltage for the circuit given below. For an op amp, specified values of input offset voltage VIO is 4 millivolts and the input offset current IIO is 150 nanoamperes. If somebody asks, then you are in a position to immediately calculate the total offset voltage, because you know how to get from VIO the output offset voltage. You also know how to calculate the output offset voltage using IIO, the input offset current. Here the feedback resistor is 500 kilo ohm and R1 is 5 kilo ohm, that is what you should remember. So, what is the offset voltage? The offset voltage due to VIO is VIO multiplied by the gain. The gain here is R1 plus RF by R1, which is 5 kilo ohm plus 500 kilo ohm by 5 kilo ohm, and when you multiply, it is almost 101 I think, and multiply by 4 millivolts gives me 404 millivolts. This 4 millivolts is the input offset voltage given in the problem. So, you get 404 millivolts as the offset voltage due to input offset voltage alone. Now, we also should calculate what is the contribution to the output offset voltage due to the input offset current IIO, and the formula is VO, or the output voltage offset due to input bias current, is nothing but input current offset multiplied by RF, the feedback resistor. 150 nanoamperes is the value of the input offset current multiplied by 500 kilo ohm, which is the value of the RF, and when you multiply you get 75 millivolts as the answer. So, you have now independently calculated what is the output offset voltage due to input offset voltage alone and due to input offset current alone. The total offset voltage is a sum of these two. So, total is 404 millivolt due to input offset voltage plus 75 millivolt due to input offset current, and the total is 479 millivolt, which is the answer for the problem. So, you can see that by knowing very simple relationship between the output and the input, in these cases one can actually measure input offset voltage, measure input bias currents also, and then try to find the input bias current and calculate the contribution for the output offset voltage from these two sources. Right, now we will actually move into the next stage and try to find out how to measure input bias current. It will be good to measure input bias current corresponding what is the current flowing into the positive terminal and the negative terminal at the input. Right. Now, how do you define the input bias current IIB? Now, IIB plus and IIB minus you are already familiar with are the two bias currents flowing into the plus and the minus terminals of the amplifier. Therefore, IIB is the average of these two currents, IIB plus IIB minus divided by 2. We have already also seen that these two currents ideally should be equal, but in reality they need not be equal, and that is why we take the average of the two currents. So once you know this, you can also determine what is the separate input currents flowing into the each of the terminals. So from this equation you can obtain IIB plus is nothing but IIB plus IIO by 2. If you know the input offset voltage and the input bias current, you can actually calculate what is the input bias current through the plus terminal and what is the input current through the minus terminal. The input current through the minus terminal is again IIB minus IO by 2. Okay, now let us try to do a simple illustrative problem. Calculate the input bias currents at each input of an op amp having specified value of input offset current IIO 5 nanoamperes and IIB 30 nanoamperes. So the average of the two input currents is 30 nanoamperes and the difference is 5 nanoamperes. So what IIB plus we know is nothing but IIB plus IIO by 2, that is equal to 30 nanoamperes plus 5 nanoamperes by 2, that is 32.5 nanoamperes, and IIB minus is with the negative sign here, that is 30 nanoampere minus 5 nanoamperes by 2, that is 27.5 nanoampere. So these two are the individual bias currents flowing into the two terminals, and the average of this is 30 nanoamperes, which is the input bias current, and the difference between these two is about 5 nanoamperes, that is the input offset current. So if they give 2, they ask the third one, it is very easy for us to calculate what the value is. Now let me go back and show you how to measure input bias currents. So here I have the circuit, operational amplifier circuit, where I have again used 1 megohm for the feedback and 100 kilo ohm at the R1, and I have also connected another 100 kilo ohm to the ground. The terminal 3 is connected to the ground. Now what I want to measure is what is the input bias current flowing into this and what is the input bias current flowing into the other plus terminal. These two input bias currents I want to know. The simplest method is to actually measure the output voltage, and by using a multimeter you can measure what is the voltage here and what is the voltage at this pin, exactly at the pin number 2 with reference to ground and pin number 3 with reference to ground. So you know the voltage divided by this resistance gives you the current. So that is what I am going to now do. So you can see the corresponding op amp circuit is shown below in the breadboard. You have the op amp and the different resistors are connected exactly in the same manner shown here, and now what I am going to do is I am going to take the multimeter output and connect it to pin number 2 and measure what is the voltage at pin number 2. You see I have put it in millivolts, 200 millivolts range, and the output and the voltage measured is minus 4.7. This is 4.7 millivolts. So the voltage at pin number 2 is minus 4.7. Therefore what is the input bias current? The input bias current is minus 4.7 divided by 100k. That is the corresponding. So it is 0.047, that means 47 nanoamperes is the current that is flowing into this. So we can easily calculate by knowing the voltage and the resistance, we can calculate the input bias current. Now what I am going to do is I am going to remove the multimeter connection from pin number 2 and connect it to pin number 3. So I remove it and connect it to pin number 3, and if you see the multimeter now, you find the voltage is 3.7 millivolt. Again it is minus 3.7 millivolts, and so the input bias current corresponding to the non-inverting terminal pin number 3 is 3.7 millivolt divided by 100k, which is again about 37 nanoamperes. So you have about 37 and 47 nanoamperes, and the difference, which is called the input bias current offset, is 47 minus 37, so it is about 10 nanoamperes. In the example that we saw, it was about 5 nanoamperes they are given, so it is of the same order, it is about 10 nanoamperes, that is a input offset current that we have. That means the difference in the current between the two terminals corresponding to inverting and non-inverting terminal. So it is very easy to measure the input bias currents, and if you want to know what is a input bias current, you find the average of 47 and 37 nanoamperes. That gives you the average input bias current, and the input offset voltage is the difference. So we can calculate the input bias currents and the bias current offset. So now we will move on to the third characteristics of the op amp, which is basically input resistance. We have also seen, if you recall, in one of the earlier lectures, how to measure the input resistance and output resistance of any amplifier, usually the transistor amplifier. I remember I also showed a demonstration of the actual measurement of input resistance of an amplifier. Usually not many people know about this in general, so it will be good to again go through this exercise and try to understand how to measure the input resistance of a given operational amplifier circuit. What do you mean by input resistance? Input resistance is input voltage divided by the input current in principle. It is a input voltage divided by input current. The input resistance of a open loop configuration of an op amp is in the order of megohm, about 1 or 2 megohm will be the manufacturer's specification, and as a matter of fact it can differ from one operational amplifier to another. In general it will be a very large value. We all know that for a good voltage amplifier the input resistance should be very large. We have seen it many times in the earlier lectures also. Now how do we measure the input resistance of an op amp circuit? Say a non-inverting amplifier shown below. So I have taken an example to explain to you how to measure the input resistance of a given configuration. What I have here is a non-inverting amplifier with RF and RI, and the input is given at the pin number 3 or the non-inverting terminal. You know the output voltage is equal to V in multiplied by 1 plus RF by RY, which is the corresponding to the non-inverting amplifier. Now what I am going to do is I am going to add another resistor at the input, which is a variable resistor of several megohms. Invariably it is of very high resistance. That is what is shown in this figure. You can see it is a variable, Rx is a variable resistor. So it can go from some 0 to a maximum value of 10 megohm or whatever. If you have such a potentiometer or a variable resistor, this experiment can be easily done. Now to measure Rin, what you do is first initially you keep Rx equal to 0. That means you are almost shorting this. There is no resistance here, 0 resistance. So V in and V3 are equal. Keep Rx equal to 0 and now measure the output voltage. So the entire voltage is available at pin number 3 or at the non-inverting terminal, and output voltage is now measured. Now what I do for a given input voltage, now what I do, I do not disturb the input voltage or any of the other components in the circuit. I only start increasing using the variable potentiometer, the knob. I keep increasing the resistance till I get an output voltage which is half of the previous value that I measured with Rx equal to 0. So all that I do is I keep increasing the value of Rx till I get an output voltage which is half the previous value, keeping the V in constant. I do not change the V in at all. Now what I know is whatever is the input voltage, it will be multiplied by the gain and I will get the output. If the output voltage has become half of the previous value, that obviously means that V3 has become half of V in. The voltage at point V3 has become half of the voltage at point Vn. That is what we understand when we get half the voltage. When will this happen? When will a voltage divide equally? It will happen only I have two resistors which are of equal value. If I have 200k resistors connected to 5 volt, if I measure the voltage across the one of the resistor, you would find the voltage will be 2.5. This resistor is basically a linear device, and therefore you would find the total voltage is split into half, and each of the resistors drop equal values of voltages, which is V by 2. Therefore, this will happen when the two resistors are equal. One resistor is the external resistor that I have deliberately connected as a potentiometer, and the other resistor is the internal input resistance that is coming at the input terminal. Therefore, you find if I measure V0 by 2, at that time I disconnect my Rx from the circuit and measure using a multimeter what is the value of the resistor, and that resistance is the resistance of the input resistance of the amplifier. So, this is an indirect method of measuring the input resistance. This is called half deflection method. You would have done it in several other similar situations. When you want to measure the resistance of the galvanometer, you cannot use a multimeter directly, because multimeter has got a big battery inside and it will drive a large current and it will spoil the galvanometer. So, when you want to do, you would have done it in your high school, to measure the resistance of the galvanometer, you will always have a finite current through them by adjusting very small voltage source, and then you will introduce a resistance in the circuit till you get half the current, and then you conclude that whatever resistance that you have now included in the circuit should be equal to the resistance of the galvanometer, and that is the method of half deflection. So, you understand, you first apply a voltage with Rx equal to 0, measure the output voltage, and keeping the input voltage constant, only change the Rx, increase the value of Rx till you get half the value at the output, and then whatever is the value of Rx which you measure after, you should not measure the value of Rx in the circuit, because there will still be voltages coming at different points. So, any measurement will have to be done in a passive condition. That means either you should remove the Rx, preferably it is better to remove the Rx and then measure using a multimeter, thereby you would be able to get what is the input resistance of the amplifier. Now, due to various reasons, usually the input resistance of an amplifier like a non-inverting amplifier, you know, can be very high, so sometimes 100 megohm, 50 megohm and things like that, because the open loop gain is very large value, we have already seen that. So, when you make the gain very small, whatever is the difference between the actual gain and the open loop gain will be the factor by which the input resistance, the bandwidth, etc. will be increased in the case of op amp due to the feedback configuration, and therefore usually the value of input resistance can be very large, immeasurably large. Therefore, in an actual laboratory condition, you would find it is very difficult to get very large value megohm variable resistor potentiometer. Therefore, I am trying to suggest to you a much simpler scheme by using the same principle. So, what I have done is, now I have introduced a fixed resistor Rx here instead of variable resistor. So, now what I do is apply the input voltage directly to V3, that means you eliminate Rx, that means keep Rx 0 and measure what is the output voltage. After that, you introduce this Rx and give the input at the input terminal of Rx, and now measure what is the output voltage. So, from these two measurements you would be in a position to find out what is the you can actually trim the value of Rx by introducing different higher values of fixed resistors till you get half of the previous value, which is equivalent. Instead of directly using a potentiometer, you keep trying different values of resistors by increasing them in value till you get very close to half the thing. But in principle, you will not be able to get a precise value of fixed resistors to get the exact value of the input resistance. Therefore, we can also evaluate from the circuit what should be the input resistance if I measure an additional voltage which is V3 in the circuit here. So, if I measure V in, V3 and V out, I will be in a position to, because you know the Rx and R in are in series and V in is the total voltage applied, V3 is the voltage at the midpoint of these two resistors, and if I know that, I can calculate what is the actual ratio of the two resistors, and if I know one of them, I know what R in is. Rx I know because I only connect it in the circuit, and therefore I know Rx, I can evaluate what is the value of R in. So that is a scheme I am trying to explain to you. Now in this circuit that you have got, what is a current? I in. I in is V in divided by the total resistance. The total resistance is Rx plus the R in, which is the internal resistance in which we are interested. V in divided by Rx plus R in is I in. It is also equal to the difference between the two voltages at the end of Rx, V in minus V3 divided by Rx. The change in voltage divided by resistance gives me the current through the resistor. This is also simple expression of Ohm's law. So from, if I now simplify this expression, V in by V in minus V3 into Rx, by rearranging this equation, that gives Rx plus R in, and therefore R in is Rx multiply R in by V in minus V3 minus Rx. You can further simplify the mathematical expression, and you can get R in from V3 Rx V in minus V3. All these quantities are known, are measurable, and therefore you can measure them and calculate what is R in. So this is again another thing that I wanted to show you. Before I actually go into that, I want to show a simulation of the measurement. So you have here a board in which the op amp is sitting at the center. You can see the op amp. This is a printed circuit board in which the op amp is there, and you have some gaps which you can fill, and I will now do auto setup, so that you can see I have put a variable resistor here, I have put a fixed resistor here, R1, this is R2, and the wiring is completed by using two multimeters and a dual supply and a voltage source, etc. So what is that I have to do? First, keep the resistance 0. You can see the wiper is at this point, that means there is 0 resistance here. With the 0 resistance, I will apply some voltage. I will switch on the power supply now, all the power supply and the multimeters. Now I switch on some, let us say 1 volt. I have given 1 volt now. You can see the output voltage is 1 volt. Now what I do is I keep on increasing, because the output voltage is 1 volt, because both the resistors are 10k 10k equal. So that is why I am getting 1 volt. Now what I do is I will keep increasing the resistance till I get a 0.5 volts across. Now it is 0.5 volts. So this multimeter measures the voltage at V3, this multimeter measures the voltage at the input, and therefore when it is 0.5 volts, then you know the value of the resistor that I have here in the variable resistor is the actual value of the internal resistance of the op amp. So in order to measure, I will just go to measure with resistance. You see that is disconnected from the circuit, and the resistance is measured using another multimeter, and it shows around 5.1 megohm. So 5.1 megohm is the input resistance by this half deflection method. That is what we have now measured. So having seen this, let me quickly go on and show you an actual measurement on the laboratory table. So here I have a voltage source, which actually is a millivolt source, which we have used earlier also in many of our demonstrations. This is a millivolt source, and the millivolt source is connected at the input of this amplifier, which is the same amplifier which I have shown you just now. Instead of 10k I have used 100k here. They are equal value, and I give the input voltage here from the millivolt source, and I measure the output voltage, and then I introduce the Rx here of an appropriate value, so that the output is up near about half the value. If that happens, then Rx should be equal to R in. That is a principle. Now I get about 0.495 volts. This is in 2 volts range, and therefore 0.495 or nearly 0.5 volts is the voltage that I measure at the input. That means this gives you around 500 millivolts or about 0.5 volts. Now I take it out and connect this at pin number 3. So the voltage here is around what I would do is perhaps I will connect it at the pin number 6 and find out what is the output voltage. So the output voltage is minus 400, about 400 millivolts when I give the input at this point after the resistor. Now what I do is I will take the input and give it at pin number 3 itself. So I have actually given the input at this point at pin number 3 directly. I have given the input from the millivolt source at this point pin number 3, and I measure the output voltage using the multimeter. It is about 1 volt, 0.99 volt. Now what I do is I remove this input and connect it at the input point before the resistor. So from here I disconnect the input voltage and connect it here. Now what you get? You get about half of that, 0.573. It is not exactly half but very close to half, and that shows that whatever resistor I have connected here is approximately equivalent to the input resistance, and that is why this actually, if you look at, this is about 4.7 megohm and this is about less than about 100 kilo ohms. So it is about 4.6 megohm. So 4.6 megohm is very close to the input resistance of this configuration, because when I connect it at the pin number 3 I get about 1 volt, when I connect it at this point I get about 0.5 volts, and therefore it is half of the previous value, and therefore this resistance that I have now introduced should be equivalent to the input resistance of the op amp. So by this you will be in a position to measure the input resistance of any amplifier by using this principle. Thus we saw 3 different characteristics of the operational amplifier: the input offset voltage, input bias current, and input resistance, and also how they can be measured actually in a laboratory by actually using the different configurations. Thank you.